Hi everyone, I'm Mrs. Fitzpatrick, and today we're going to be talking about the logistic equation, specifically looking at cases that are modeling real world situations that involve maybe a carrying capacity. And we're going to kind of use our knowledge of differential equations that we learned in 10.1 and 10.2 to do these kind of more application focused problems. So let's get started. The simplest model for population growth is dy dt equals k times y. It essentially means that it's growing proportionally to this growth constant. And so, according to which it actually ends up growing exponentially. And we'll see why this is when we actually solve this differential equation. So, this may be true for a short period of time. However, no population can increase without a limit. And so that's where carrying capacity kind of makes it a little bit more complicated. So, to take this into account, population biologists actually use the differential equation dy dt. We actually do this in black because I want to color code what some of the variables represent. Okay, so we have dy dt is equal to k times y. It's the general premise, but we need to take into account that we can't just keep growing as a population. That just is not realistic. So they modify it to be times 1 minus y over, we're going to use capital A. And let me kind of give you an idea. So just like in a previous unit, K is your growth constant. And then A actually ends up giving you the carrying capacity. So A is the carrying capacity. And no, A is greater than 0. And in this case, because what we're talking about is population growing to a carrying capacity, we'll have your K also be greater than 0. Okay, so now what we're going to do is we're going to solve this differential equation. This is a little bit complex. And so if you haven't done partial fractions in regards to integration, you might want to brush up on that before you watch the whole thing through. But we're going to go ahead and jump right in. So dy dt equals k times y times 1 minus y over a. And we're going to solve this sucker. Okay, so what we need to do first is we need to split up our variables, just like we've done in previous units. So what I'm going to do is I'm going to divide both sides by y times 1 minus y over a. So I end up with 1 over y times 1 minus y over a. And we have a dy on that side equals, and I'm going to multiply, I like to say multiply in parentheses, it's not really what you're doing, both sides by dt. So we have k, remember there's still a k there hanging out, dt. And then we can integrate both sides to solve this differential equation. Okay, now what we can do next is we can take this piece right here. I'm going to do this in another color off to the side. This, we're going to have to do some partial fraction work. And so we want to figure out how we can rewrite 1 over y times 1 minus y divided by a as a over, let's see, well, let's actually do a little bit of algebra first before we deal with this. So let's go ahead and we're gonna be a little sneaky. We're gonna do some rewriting first. I'm gonna rewrite this as 1 over y times a over a minus y over a. I'm going to try to find a common denominator, combine some things in the denominator first. So I end up with 1 over, let's see, y times a minus y all over a. Okay. Now, what I can do is I can rewrite this as, oh, we can pull out an A. And let's see. Yeah, so I'm going to pull out an A. We have what 1 over, and let's see, let's actually pull out a negative 1 over A. And that's because I want to flip-flop that A minus Y situation. So we end up with negative Y over A times Y minus A. Okay, so let's keep going from here. So what we want to do, looking at this, notice that I can multiply that bottom fraction by the reciprocal. So I actually end up with negative A over Y times Y minus A. And so there was a lot of algebra in there. So make sure you go through those steps thoroughly so you can kind of see how I got there. And now what we're going to do is we're going to use partial fractions. So we have negative A over Y times Y minus A, and we want to break this up into B over Y plus C over Y minus A using those partial fractions. Okay, so the way we do this with partial fractions is we can essentially find our common denominators, right? So I'd take B over Y, I can multiply by Y minus A over Y minus A. And then I would take C over Y minus A and multiply by Y over Y. I'm gonna throw some parentheses around that. So I end up with negative A is equal to B times Y minus A plus C times Y. Okay, now we can let Y be whatever we want. And so to get rid of one of these variables, we can let Y equal 0. So let Y equals 0. Then I end up with negative A equals B times 0 minus A. Negative A then equals negative A times B divided by negative A, and B equals 1. How nice is that? Okay, now we also want to figure out what our C is. So I'm going to let Y equal A because that will get rid of B for me. So I end up with negative A equals B times A minus A is 0, so that term's gone, plus C times A. Divide by A, and C actually equals negative 1. Okay, so doing all this algebra, and you can see why I did this off to the side because it's a lot, it's very involved. We can go ahead and say that negative A over Y times Y minus A is equal to B, which is 1 over Y, plus C, well, it's negative 1, so I'll do minus 1 over Y minus A. Okay, so this integral actually isn't bad once you do that. It's the integral of 1 over Y minus 1 over Y minus A dy is equal to, and the integral of K is just K times T. Don't forget your plus C. Okay, the integral of 1 over Y is just the natural log of the absolute value of Y minus, we have the natural log of the absolute value of Y minus A, which equals KT plus C. When you subtract logarithms with the same base, you can divide to condense. So we have natural log of the absolute value of Y over Y minus A is equal to KT plus C. We have e to the power of those. We end up with Y over Y minus A is equal to e to the KT plus C. Okay, you can actually rewrite this as Y over Y minus A equals C sub 1, right? E to the KT. That's because you could rewrite e to the KT plus C as e to the KT times e to the C. E to the C is just another constant. Okay, We're almost there. So now what we want to do is we want to solve for y. And so we can multiply both sides by y minus a. We can distribute that. So y equals c sub 1 e to the kt y plus c sub 1 e to the k, oh, minus c sub 1 e to the kt times a. Okay, we can move the one with y still to the other side. Move this up here. So we have y minus c sub 1 e to the kt y equals negative a c sub 1 e to the kt. I'm running out of space. Okay, and then we can factor out a y. We have 1 minus c sub 1 e to the kt equals negative a c sub 1 e to the kt. Okay, we're almost there. Divide to get that y alone. And we have y equals negative a times c sub 1 e to the kt over 1 minus c sub 1 e to the kt. Okay, and what we can actually do, and usually the way you see this general solution written, if you memorize the formulas, if you do a little bit of algebra and simplify it a little bit, oftentimes you'll see it written as y equals a over 1 minus e to the negative kt all over c. And I guess in this case we use c sub 1, right? We used a sub. But that's it. Now, if there's actual numbers in there, it's a little bit easier to handle, but it's still kind of a similar idea where you have to use partial fractions to do that integration for the logistic equation. Okay, so let's now take a look at an example. So we're going to solve dy dt equals 0.3 times y times 4 minus y with the initial condition y of 0 is equal to 1. Okay, so we have dy dt is equal to 0.3 y times 4 minus y. And they did give us an initial condition, but we're not going to use that quite yet. Okay, so what we need to do is this actually almost looks like what we were using prior, right? With our k times y times 1 minus y over a. I'm going to actually write that out off to the side. And let's see if we can actually rewrite this so that we get it in this form. So notice what you can do to get it in this form is we can factor out a 4 from the 4 minus y. So what that looks like is dy dt is equal to 0.3y times 4, because we're pulling out a 4, times 1 minus y over 4. Notice if I distribute that back in, it's still equivalent. And so now what we have is dy dt is equal to 0.3 times 4 is 1.2y times 1 minus y over 4. This actually gives me, all of these variables. So I know that k is 1.2. I know that a is 4, right? And so it's following that logistic model that we were talking about. And we actually have the solution to this differential equation. We have it up here. I'm going to write it again. Y equals a over 1 minus e to the negative kt over c sub 1, so whatever your constant is. And so y is going to equal, our a is 4, all over 1 minus e to the negative 1.2t divided by c, and we need to just solve for c. So we're going to plug in 0 for x and 1 for y. So we have 1 equals 4, oh, and I guess it's t, sorry, 4 over 1 minus e to the 0, right, which is just 1 over c. And then we can solve from here. Well, if this fraction equals 1, it means the fraction numerator and denominator need to be equal. And e to the 0 is just 1. Subtract 1. 3 is equal to negative 1 over c times negative 1, or divide by negative 1. Negative 3 equals 1 over c. That means c equals negative 1/3. And so your solution to this differential equation is y equals 4 over 1 minus e to the negative 1.2t divided by negative 1/3. Well, dividing by negative 1/3 is the same as multiplying by 3. So you can actually write it as y equals 4 over 1 plus 3 e to the negative 1.2t. So I would recommend memorizing the solution to this differential equation. It just makes these problems a lot more simple. Not saying you can't solve those differential equations, it just takes a lot of work, like I showed you in that previous example. Okay, let's take a look at number 2. So it says a deer population grows logistically with growth constant k equals 0.4 per year in a forest with a carrying capacity of 1,000 deer. Find the deer population p of t if the initial population p sub 0 is 100. So it gives us k is equal to 0.4, a is equal to, 1,000. That's our carrying capacity. And the initial population is 100. So it did give us an initial condition. So using this, we can actually figure out our general solution to this. So we end up with y equals a, which is 1,000, divided by 1 minus e to the negative k is 0.4t divided by c. And all we have to do now is solve for c using that initial condition. So our initial condition is 100 is y equals 1,000 divided by 1 minus e to the negative 0.4 times 0 divided by c. And so we end up with 100, oops, not 1,000, 100 equals 1,000 divided by 1 minus e to the 0, in that case is 1 over c. You can multiply both sides by 1 minus 1 over c. We end up with 100 minus 100 over c is equal to 1,000. What you could do here, it's up to you. You could just subtract 100 and then cross multiply to get the rest, or you could divide everything by 100 to make it a little more simple. I'm just going to subtract 100. I'm going to move this up here because I'm running out of space. I end up with, let's see, negative 100 over c equals 900. We can, let's see, cross multiply. So 100 equals negative 900c. Divide by negative 900. And it looks like c equals negative 1/9. And so then when I plug that in, and actually it's p of t is what it's called, so I'm going to rename it from y to p of t, equals 1,000, which is our carrying capacity, over 1 minus e to the negative 0.4t. Dividing by negative 1/9 is the same as multiplying by negative 9. So it's actually plus 9e to the negative 0.4t. Now, once you get this equation, you can utilize it in the next problems in order to solve it. So it says, how long does it take for the deer population to reach 500? So you're just gonna, since this equation models the population of the deer at time t, you just plug in 500 for p of t, and then you can use that to solve for the time. Okay. And so you can cross multiply here. We get 500 plus 4,500 e to the negative 0.4t is equal to 1,000 minus 500. We end up with 4,500 e to the negative 0.4t is equal to 500. Divide by 4,500. And e to the negative 0.4t equals, well, 500 over 4,500 reduces down to 1/9. We can then take the natural log of both sides. Okay, let's go ahead and move this up. We end up with negative 0.4t equals natural log of 1/9. Divide by negative 0.4. Notice I'm not rounding yet. T equals natural log of 1/9 divided by negative 0.4. And now I'm going to go ahead and punch that in my calculator and round, and we get approximately 5.493. Now, whenever it is an application problem, you want to include units. So I'm going to say it will take about 5.493, and it's going to be years, I believe, is the, yep, per year. So years for the population to reach 500. Okay, so you can see why memorizing that equation, the solution to that type of model, logistic model with a carrying capacity, is really in your best interest, because it can get very, very complicated to solve those differential equations. Okay, let's see what we have next. Okay, so I'm going to let you guys work on numbers 3 and 4. It's about the same as what we've just done. And so go ahead, work on 3 and 4, and then you can check your work using the solutions on my website, which is mrsfitzmath.com. And all of the solutions should already be uploaded for you to view. All right. That is all. Thank you.